In this video, we will see what surface tension is, how it can be defined, what is surface energy, what will be the expression for surface energy. Hello everyone. So today we are going to see a very interesting phenomena happen in nature, that is surface tension. Now what this surface tension is, before going to that, I will ask you a few questions. All of you might have seen that in nature, why these droplets always gets the shape of a sphere. You might have seen them. See what happens. These liquid droplets, they will acquire a shape of almost spherical. Why? Why is that so? See, if you exclude the effect of gravity, then they will be a near perfect sphere. So what is the reason for that? If we talk about a special water strider, this is an insect. This is insect known as water strider. So you know what is the specialty of this? It can easily walk. It can easily walk on water. So this is important. How these insects, special kind of insects, they are able to walk on water, not swim. Swimming is different than walking. So they can actually walk on the water. So what is the reason for that? Let me give you one more example. So this I will show you that this is some kind of needle and it is actually floating on water surface. This is made up of, this needle is floating on water surface. How? So it is not always that needle will float on this, but there can be certain arrangements with the help of those we can float a needle on water surface. So we will try to find out the reason for all these things, and that is nothing but the surface tension. Surface tension is the answer for all our phenomena occurring in nature. So we will extend our analysis to two molecules. There are two molecules present. So one is at the surface. Obviously, as you can see, this is at the surface and this molecule is at the bottom, deep inside the water, right? So remember, this is microscopic view of two molecules which are situated, one at surface. This molecule is at surface, as you can see, and this is deep inside the liquid. So when you see this, then what will happen? Now this is surrounded by, this molecule is actually facing the force of attraction from its molecules in surrounding area from all the sides, while the molecule which is at the surface, if you see, so this is only having this force inside the liquid, not above it. Why? Because here atmospheric air exists, but here this is liquid. So we know that cohesive forces, they are much more in liquid. In liquid, it has to be more in comparison to air. So air is not going to attract this molecule towards outer boundary. So what will happen? So because of that, what happens? It tries to, this molecule, it gets attracted by another molecule in surrounding, and you can see like this. There can be many other molecules which will be attracted by this. So what happens? They try to minimize the surface area. They try to minimize the surface area. Now we should keep this in mind that this is only the front view. If you talk about, if you talk about the top view, then how top view will be shown. So let me show you. Now suppose we have a top view in shape of this circle. Now there are various molecules. There are various molecules like this. There are various molecules like this. And what will happen? There will be some force of attraction. Like these molecules are attracted, these molecules are attracted, these molecules are attracted, they are also attracted, they are also attracted, they are also attracted. Like this, they will be attracted towards each other. Now, it is not the case that there will not be any surrounding molecules. Obviously, there will be other molecules as well. So, if it is the case, they will be attracted towards each other like this, like this, like this, like this, like this. So, ultimately, what happens? They try to minimize their surface area. Where? Surface area at liquid air interface, right? So this interface is important for us. Whenever a liquid comes in contact with any air or any gas, then it is the property of liquid. So keep this in mind, that because of this, they try to minimize their surface area. They form a bubble kind of shape or spherical shape. Now, why spherical shape? Because you should know that a a sphere has minimum surface area for a given volume. You should keep this in mind. Sphere has a minimum surface area for a given volume. This is the reason. Now, moving on to words, how we can put up this phenomena in word. So we should know that liquid droplet behave like small balloons filled with liquid, and the surface of liquid acts like stretched elastic membrane that I have already shown you in form of that top view under tension. Now, the pulling forces that causes this tension acts parallel to the surface and is due to attractive forces between the molecules of the liquid. Those are called cohesive forces. The magnitude of this force per unit length is called as surface tension or coefficient of surface tension. So we should keep this in mind, that surface tension, it can be denoted by the symbol sigma, and sigma, if you want to write, it will be force per unit length. So this is basically F upon L. The unit will be Newton per meter. So you should keep this in mind, that the surface tension will be denoted like this. Sigma value is equals to F upon L. Unit will be Newton per meter. So we should keep this in mind. Now we will see the work done in stretching a liquid film and how surface tension can be expressed in terms of work done. So as you can see here, this is air, this is liquid film, and again this is air. So we are interested in finding out the work done and relating it with the surface tension. So we can see that if we want to stretch it, now see this liquid film, if you want to stretch, then we need to do some displacement. So suppose we apply the force F and it is displaced by this area. Look at this. We apply the force F and the film is displaced by this distance, which is delta x. So what we can write here, because there are two interface, air liquid, this is one interface, and liquid air, this is second interface, as we can see here. So surface tension will be acting on this length is b. So we can write here sigma s into b, and here also sigma s into b. So the F value, the force F can be given as sigma s into b plus sigma s into b, that is 2 sigma s into b. Now when we talk about the work done, so remember work done is equals to force into displacements, that in this case is delta x. So remember, this is the work done required. to increase the area. Which area? This shaded area. This area if you want to increase, so work done required in increasing this area will be F into delta X. Now let me put it in the numerical form so that work done can be expressed as this is equals to, it will be stored in form of energy. So this is energy, sometimes also known as surface energy, is equals to F into delta X. Now we can see the value of F is this 2 sigma S into B into delta X. That can also be written as sigma S into twice B into delta X. So from here, what we can write? We can write that sigma S value can also be expressed as energy required per unit increase in surface area. Remember this is very important expression because surface tension can also be expressed in form of this relation. Remember this. Now, don't get confused with this area. Some students will see, sir, why this is 2b into delta x. Now look at this. This height is b, this length is delta x. So this is only one side of area. This area is only one side of area. There is another side at the back of this. So that will be twice the area. So b into delta x into 2 will be the surface area, total surface area to be increased by applying this force F, and what is the energy required can be expressed in terms of surface tension and all. Now we will look at this surface energy as surface energy is work done in changing the surface area is the change in surface energy. So obviously the work done in changing surface area will be the change in surface energy because work done is going to stored in form of surface energy. Now energy is required to increase surface area, which we have seen, but energy will be released when surface area is decreased. So we should keep this in mind. Now the surface energy, we have already seen that surface energy is nothing but the work done or work stored. We can write like this. Now we will see the energy required in splitting a spherical drop. So now suppose let us take this drop of radius r, and here many small droplets of radius r. So we know that the volume will be constant. So volume here will be 4 by 3 pi r cube, which must be equal to, now suppose we have n liquid droplets after breakup. So this will be n multiplied by 4 by 3 pi r cube. So from here we can see that this r cube value is equals to capital R cube by n. So this is important expression because the radius we can easily determine. Now when we talk about the energy required, so remember this energy required can be expressed as the product of increase in area to the surface tension, sigma s multiplied by increase in surface area. So this can easily be given as this E is equals to sigma s multiplied by. Now what is increase in surface area? So obviously we know that if n number of droplets are there, surface area will get increased. How much? So there are n droplets. What is the area of each droplet? That is 4 pi small r square minus what was initial area? So that is 4 pi r cube. Remember this. This is the expression which can be used to determine the energy required in splitting a liquid droplet. Right? So that's all for now. Thank you.